Let's dive right into this explainer and explore the fascinating engine that actually teaches modern AI how to learn. Just think for a second about the sheer scale of global computing power right now. We're talking data centers consuming gigawatts of energy, all largely dedicated to running these massive, relentless optimization loops. You hear it all the time, right? Neural networks and machine learning models are training on massive data sets. But how exactly does that training work under the hood? What's the actual mathematical mechanism driving that multi-billion-dollar process? Well, today we're exploring continuous optimization, which is absolutely the bedrock of machine learning. To get a grip on this, I want you to imagine being a blindfolded hiker dropped onto a massive, incredibly uneven mountain range. Your one and only goal? Find the absolute lowest valley. The catch is, you can only do this by feeling the ground beneath your feet. You can't see the whole map, and obviously, you can't just teleport to the bottom. You literally have to take it one careful step at a time. In our case, this mountain range is a model's error surface. Every careful step represents the AI tweaking millions of internal weights and biases to find the lowest possible loss. It doesn't know the answer right away. It has to physically feel its way down to the lowest possible error. All right, let's establish the ground rules in Section 1, the optimization landscape.
So the really crucial point here is that our AI isn't just picking from a multiple choice list, it's smoothly adjusting its styles. In continuous optimization, we're navigating a totally continuous mathematical space. The algorithm is hunting for the best parameters to minimize its error. Unlike a discrete optimization problem like, say, the famous traveling salesperson routing puzzle where you jump between distinct, completely separate cities, continuous optimization deals with real fluid numbers. This allows for smooth, calculated derivatives, so the algorithm can basically seamlessly slide down the error surface to find that perfect minimum value.
Moving right along to Section 2, Unconstrained versus Constrained Optimization. On one hand, we have unconstrained optimization. This is exactly what it sounds like. It gives the algorithm the total freedom to roam completely unchecked across the entire mathematical landscape to find the deepest valley. But in the real world, we actually often use constrained optimization. This is where we introduce strict mathematical rules and fences that the algorithm just cannot cross. A great example of this is L1 or L2 regularization. You might know them as lasso or ridge regression. These act as a literal mathematical fence to penalize overly large weights and stop the model from overfitting to the data. The algorithm is still desperately searching for the lowest point, but being restricted by these boundaries drastically changes the path it has to take to get there. Which brings us to the star of the show, Section 3, the gradient descent algorithm. Enter gradient descent. This is an iterative numerical procedure that finds a local minimum by repeatedly taking steps in the direction of the negative gradient. Now, don't let the math jargon throw you. Negative gradient is literally just the formal term for the steepest downward slope. Why do we do it this way? Well, calculating the perfect bottom of the valley all at once for a modern large language model would probably require a computer the size of the known universe. The math of these complex models simply does not allow for an instant algebraic answer. So instead, we rely on gradient descent to mathematically feel the slope under its feet and just step in the opposite direction of the incline. The basic loop is actually brilliantly simple. Step 1, evaluate the gradient, the slope, at your current position. Step 2, take a small step in the opposite direction of that slope. Step 3, reevaluate the new slope at your new location. And finally, step 4, just repeat that until you hit the bottom. It is a highly logical, step-by-step process. Feel the slope, take a step downhill, and repeat until the ground totally flattens out. When it's flat, that tells the AI it has finally reached the minimum error. Now for the tricky part. Section 4, choosing the step size. This brings us to a parameter you are going to hear about constantly in machine learning, the learning rate. The learning rate is exactly what dictates the physical size of your step. If our learning rate is too tiny, well, the AI takes microscopic steps. It could take millions of iterations to learn anything at all, wasting an incredible amount of time and expensive computational power. But if it's too massive, we risk bounding right over the minimum, shooting straight up the other side of the valley and making things entirely worse. It's a classic Goldilocks problem. To handle this in modern practice, the learning rate usually isn't static. We often use learning rate schedulers to start with large, ambitious steps and then gradually take smaller, more refined steps as we get closer to the bottom. When the step size, that learning rate, is poorly tuned and just a little too large, the algorithm aggressively overshoots the lowest point with every single step. Instead of smoothly walking down, it bounces violently from one steep wall of the valley to the other, barely making any real progress toward the center. It's chaotic, it's incredibly inefficient, and it's exactly the kind of behavior we want to avoid when training a model. So to speed things up and avoid getting stuck, especially when we're dealing with massive data sets, we have to rethink how we calculate that slope. Batch gradient descent uses the entire dataset to calculate the perfect, most accurate slope before taking a single step. That's highly precise, but brutally, painfully slow. So we swap to stochastic gradient descent, or SGD, which uses just one data point at a time. It trades perfect accuracy for rapid, noisier steps. However, pure SGD using literally one single data point is almost never used today. The actual industry standard is mini batch gradient descent. By using small, manageable batches to estimate the slope, we hit the perfect sweet spot between computational speed and gradient accuracy. And actually, that slight bit of noise helps the algorithm bounce out of bad spots while getting down the mountain much faster overall.
And that leads us perfectly into Section 5, adding momentum.
I absolutely love this quote from Tom Mitchell's foundational book on machine learning. He writes, "The gradient descent search trajectory is analogous to that of a momentumless ball rolling down the error surface." This perfectly captures the biggest vulnerability of basic gradient descent. Without momentum, the absolute second the ground flattens out, even if it's just a tiny, shallow ledge and not the true bottom of the mountain, the ball just stops dead. The algorithm thinks, great, I'm done, but the true minimum is still miles below. So how do we fix it? We add momentum. This is a brilliant algorithmic upgrade that literally remembers its previous steps. By mixing in a fraction of our previous step's direction, we give our algorithm actual physical inertia. It acts exactly like a heavy bowling ball building velocity. This dampens those erratic, zigzagging oscillations we talked about earlier, and it allows the algorithm to smoothly roll right through tiny bumps and blast down long, consistent slopes without getting permanently trapped in small, fake valleys. As we wrap up, I really want you to consider the staggering scale of modern deep neural networks. If momentum helps us smoothly roll through small valleys on a simple 3D mountain, what on earth happens when the AI's landscape has billions of dimensions? In the latest language models, this exact same blindfolded hiker is simultaneously navigating a mathematical mountain range with billions of different directions at once, desperately trying to find the ultimate bottom. And here's the kicker. In a billion dimensions, you aren't just dealing with valleys, you're dealing with saddle points, these vast, tricky areas that are entirely flat in one direction but steeply sloped in another, which makes momentum even more absolutely critical for escaping. How do we keep that hiker from getting completely lost in a billion-dimensional maze? Well, that is a vast topic for another day, but hopefully this gives you a completely new perspective on the rigorous continuous optimization math that actually teaches machines how to learn. Thanks for tuning into this explainer.